Hello, everyone. In this video, we are going to look at the balanced and unbalanced forces on a ramp. And then we are also going to look at the uh, linear equilibrium and rotational equilibrium. And then finally, the rotational motion. So let's start with balanced forces on a ramp. So if this box is stationary on a ramp, or it might be moving at a constant velocity. So as long as the motion is with the constant velocity, that means that forces must be balanced. So what are the forces on this blue box? So there will be a gravity force or weight force that acts vertically down. Support force will be at 90 degrees angle to the ramp. And then friction force will be acting up the ramp. Now, if this object is moving downwards with a constant velocity, that means all these forces, three together, they are balanced. There are different ways to do it, but we will use the closed triangle method. And what is the closed triangle method? That we will draw these three forces so that they make a closed triangle. So let's start with, so gravity force was acting in this direction. And as you can see from this diagram, that friction force was acting up the ramp and support force, and they are at 90 degrees angle to each other. So from here, so we draw the gravity force first. From the tip here, we draw friction force that was along up the ramp. So that will be the friction force. And the third force, F support in this direction. So we started with from this point, and after adding these three forces, we have ended up here. So that means resultant of these three forces is zero, or the forces are balanced. If we draw this vector in the opposite direction, this one, first force and second force, and then we draw the resultant force in this direction, then that will be the result of these two. And that will not make them balanced, that they will be unbalanced. So in a closed triangle, arrows have to be pointing in this way, so that if we started from here, that's the first vector, first force, second force, and third force. So the third force should end up where we started. So, and once we have done the closed triangle, then we can calculate the size of the friction force or the support force, because this angle is 90 degrees. And we know that weight force is mg, so we can calculate the weight force. And F friction force is the opposite side. So friction force will be weight force mg times sine of this angle. And the support force will, in this triangle, this is the attached side. So support force will be weight force times cos of this angle. Now this angle is same. By geometry, we can show that this angle over here is same as the angle of the ramp. Now, instead of starting from here, you draw the weight force first. And then instead of drawing the friction force, we can draw the support force, because support force was acting at 90 degrees angle, and then friction force in that direction. So it doesn't matter which way you draw it, but all three vectors should end up to where we started off. So this method can be used to find out the size of the friction force and the support force. Now, next we will look at is when forces on a ramp are unbalanced. So again, these are three forces, and but because these forces are unbalanced, and if the object is accelerating downwards, or it might be accelerating upwards. So let's see, how do we do this one? So, and this one, because forces are not balanced, Okay. So what we can do is we can find the component method. Okay. So that's the gravity force. And we can divide this gravity force into two components, F2 and F1. Now, so again, using geometry, this one will be, remember, this angle is same as this angle over here. And then F2, because it is the adjacent side, so it will be FW times cos of this angle. And then F1 will be FW times sine of this angle, because F1 is the opposite side of this triangle over here. So once we've calculated F1 and F2, now F2 and support force, they will always be balanced because the object will not be bobbing up and down. And because in this case, we were told that this object is accelerating downwards. So that means over here, F1 comes out to be greater. So F1, friction force is upward. So the unbalanced force will be F1 minus FF. So that's the unbalanced force, and unbalanced force produces an acceleration, and that will be mass times acceleration. Now, for rotational motion, rotational equilibrium, what is torque? Torque is the turning effect of a force. So if this is the pivot point and you apply a force, it will make the object turn in a clockwise direction. If you apply the same force at a greater distance, then the torque or the turning effect will be greater. So turning effect is force times distance, unit is Newton meter, and direction could be clockwise or anti-clockwise. Now, rotational equilibrium is a state where an object is either stationary or it moves with the constant angular velocity, whereas linear equilibrium is when something is moving at a constant velocity. Now, let's look at this rotational equilibrium. So say, for example, there's a pivot, and that's could be a seesaw, and there are two people, Amy and Katie, sitting, and the seesaw is balanced. So that means this seesaw is not rotating, so it's in a rotational equilibrium. Now, what are the conditions of rotational equilibrium? That upward forces should be equal to the downward forces. So let's see what are the upward forces, downward forces first. So weight force of Amy will be acting downward, weight force of Katie will be acting downward, and the weight of the seesaw or the plank will be acting downwards also. So these are the three forces which are acting downwards. There would be a support force applied by the pivot, and that will be upwards. And if this seesaw is not collapsing down, that means support force is large enough to balance these three forces. So what is the condition of first condition of rotational equilibrium is that upward forces must be balanced by the downward forces or equal to downward forces. F support is F1 plus F2 plus F plan from the diagram here. Now, second rule is that the torques must be balanced. Now, Amy is creating a clockwise torque. Katie is creating an anti-clockwise torque. So if this one is not moving or it is in a rotational equilibrium, that means that torques are balanced. And how do we find torque? Torque is force times distance. So F1 times D1, and that is the anti-clockwise torque. And M is force F2 times D2, that will be clockwise torque. So these are the two basic principles. And using these principles, we can find out the forces or distances where an object should be sitting to balance the levers. In this example, Katie had a bigger mass, so therefore she was sitting closer to the pivot to balance Amy, which had a smaller mass. Now, next thing we will look at is the rotational motion. Now, if something is moving at a constant speed, around and round about this point, it might be a toy car, which is going around and around with a constant speed. Now, so direction of the motion is changing, therefore speed is changing. And if speed is changing, that means there must be an acceleration. And if there is an acceleration, that means that there must be a force. So, and that force is towards the center. Now, generally, if an object is moving in a straight line and force is applied forward, the size of the speed will increase. If the force is in the backward direction, size of the speed will decrease. However, if the force is at 90 degrees angle, then it does not change the size of the speed. It makes it change the direction only. So if the toy car is going at a constant speed, that means the force that is changing the direction is towards the center, and that's called the centripetal force. And in this case, there is a friction, and friction is supplying enough centripetal force to keep the toy car moving in a circular path. So force and acceleration, they're both towards the center. At any particular instant, velocity is always along the tangent to the radius. And what is the equation? Equation is that centripetal acceleration is v square over r. V is the speed, r is the radius of the motion. Now, in the case of the toy car, it is friction force, that is the unbalanced force, and that unbalanced force is providing the centripetal force, and centripetal force is m times centripetal acceleration, which is mv square over r. Now, if an object is rotating in a circular path, the distance traveled is 2 pi r. So speed will be distance divided by time. Now this time is called the time period. So period of the motion will be 2 pi r over v. Now, here, this is just animation. So what are the forces acting on the car? There's a weight force, there is a support force, also called normal force, and that's the friction force. So if we start it moving, car goes and maintains a circular path. Reset. Now, let's say that there's very little friction on the road, and make it quiet. Friction is very little. So now friction is not large enough. And let's see what happens. Will it still be able to go along the circular path or not? Let's start it. So you can see it just goes along the tangent at that particular path. So that's what happens. If friction is not large enough, then the object will go in a straight line. So that was all for this video. Thanks for watching it.